Accidents happen. Transportation accidents can involve the carriers of containers used to transport highly radioactive materials, such as the spent fuel from nuclear power plants. These containers, called casks, are designed by engineers in the nuclear industry and the federal government to survive the potential hazards of transportation accidents. Casks must pass a series of qualification tests prescribed by the Nuclear Regulatory Commission and the Department of Transportation that simulate the threat that casks would face in serious accidents involving impact, puncture, fire, and immersion. When a new cask is being developed, designers must demonstrate, either with analysis, experiment, or both, that it can survive the impact conditions of a 30-foot drop onto an unyielding target. Other prescribed tests in the sequence include puncture, fire, and extended immersion in water. Beyond the required tests, casks have been dropped from 2,000 feet onto hard-pan desert soil in order to evaluate the effect of different targets and impact velocities. Despite such tests, and despite the fact that no cask designed for the shipment of highly radioactive material has ever leaked as the result of a transportation accident, a question frequently asked is, but how do you really know the casks would survive actual accidents? To answer that question, engineers at Sandia National Laboratories have undertaken studies to ascertain whether current analytical methods can accurately predict what will happen in very severe accident environments. The first step is to develop a mathematical model of the entire physical system, and then evaluate the model with a computer. One measures and determines weights, and describes how various sections and elements of the transportation system will react in an accident, how much force it will take to crush these elements, how much energy they will absorb, and how the container will interact with the transportation system. One strips away all extraneous elements, looks only at the basic structure, the frame, the sheet metal, the engine and wheels, the cask itself, the tie-downs. One studies the strengths of the various materials, calculates the forces of crushing or crumpling the structural elements. With this information, the computer is used to determine how fast the cask will be traveling when it reaches the massive object it impacts. Reduced to simplest terms, this is the general framework of the problem. Computers are used to obtain solutions to these problems, to tell what will happen to the various elements of the total system in a specified set of accident conditions. Using the output of the system dynamics model as the input data for the cask deformation model, the engineer can use the computer to analyze what will happen to the cask. With information on the various materials used in constructing the cask and the yellow impact limiters that absorb energy during a crash, plus knowledge of their physical arrangement and the speed of impact, the engineer can predict the extent of cask deformation. Scale model testing is one possible way of verifying the computer analysis. Tools such as a centrifuge and high-speed cameras, for example, allow a cask to be studied during a severe impact without concern for any vehicular structure around it. A centrifuge can be used to study all kinds of impacts, side-on or angle, and at various speeds. After a series of scale model centrifuge tests and mathematical predictions, it appeared that the casks would survive even extremely severe impacts without loss of containment or shielding. 3 specific transportation accident environments were then analyzed. First, by computer simulations or studies, then in a series of 1/8 scale model tests of simulated accidents. The first scale model test simulated a truck transporting a nuclear cask crashing into a solid concrete structure at 60 miles per hour. The spray is from the braking system for the rocket sled. Other tests were conducted at 70 to 80 miles per hour. All models were instrumented to measure such things as the acceleration of the cask through the time of impact. This series of close-ups shows the deformation to the casks. The second accident situation involved a grade crossing accident in which a stalled tractor-trailer is hit by a diesel locomotive traveling at high speed. The model cask was mounted across the track on supports, simulating the bed of a tractor-trailer. The scale model locomotive was propelled by rockets to a speed of 80 miles per hour. It smashed into the cask and swept it away. Here's a slow-motion close-up of what happened during impact. The cask fins were bent, and there were dents where the locomotive frame had hit, but there was no passage open to the cask interior. The third accident situation simulated a rail-mounted nuclear fuel cask involved in a high-speed train accident in which the cask car impacts a solid structure, such as a massive bridge support. In the scale model test you're about to see, the rail car was traveling 80 miles per hour at impact. Following the scale model tests, a series of full-scale tests was conducted in order to verify the accuracy of analytical prediction techniques. These tests represent an upper limit in the range of credible accidents. That is, they are severe over-tests. Here, in real time, is the 60-mile-per-hour test. The cask sustained some minor damage, but pressure tests after impact indicated that there was no loss of containment integrity. That is, there would have been no release of radioactive material. Most important, however, was the fact that the damage that occurred was similar to the damage that had been predicted analytically, the damage that had, in fact, already been seen in the scale model tests. The test allowed designers and engineers to correlate the results of mathematical computer modeling, scale model testing, and the full-scale testing of a cask on a truck. Here, in slow motion, we can compare the scale model test at the top of the screen with the full-scale test. The cask that survived the 60-mile-per-hour test was then cleaned up and readied for a second test of the same type. This one at 84 miles per hour. Results of this test also closely paralleled predictions. The cask again survived without damage serious enough to jeopardize containment of its contents. In the third test sequence, a diesel locomotive crashed into a stalled truck carrying a nuclear fuel cask. Powered by an array of 6 rockets, the locomotive was traveling 81 miles per hour when it struck the 22-ton cask. This slow-motion footage shows more clearly what happened at impact. Here, for comparison's sake, is the impact of both the scale model and the full-scale locomotives. In the fourth test, a railroad cask car was crashed into a 690-ton concrete abutment at 80 miles per hour. These shots show how the crumpling of the front end of the car's structure absorbed much of the impact energy, thus protecting the cask. Here again, there was close correlation between the results of the scale model test and the full-scale test. Following the crash test, the cask and rail car were moved to a fire test site and immersed for 90 minutes in burning JP4 jet fuel. Temperatures experienced by the cask ranged between 1800 and 2100 degrees Fahrenheit. The rail car carrying the cask eventually warped and rolled onto its side. But the cask survived more than an hour and a half of fire with no consequences that would have affected its ability to contain its radioactive contents. The full-scale tests made it clear that existing mathematical modeling techniques and scale model testing are valid and inexpensive methods of evaluating the structural properties of nuclear transport casks. Even in the event those casks were to be exposed to extremely violent transportation environments. Since these modeling and testing techniques proved valid, they can be used in the future in the design of casks and other shipping systems.